Right. So then the takeaway is that we're trying to cast all of our equations in terms of the knowns. And what are the knowns? What the knowns are the values we have already computed at the previous time step or iteration. Okay, that's the crux of the matter. Now, where do matrices enter? Is because this equation that we are seeing right over here, this is for one I at some I. Okay. So similarly, we're going to have the same sort of an expression for I plus 1, I plus 2, or for grid points 1, 2, 3, 4, 5, 6, and whatever. If you have 100 grid points, you're going to have 100 equations which are going to look something like this. So essentially, how do you compile them? You're going to put them into a matrix. So let's write that. Compiled equations for the entire domain or mesh, okay, are in the form of a matrix. Okay, so now we have gotten to why we are looking at matrices in the first place. Then, now that we've gotten our matrix, then we will look at this ax equal to b is equal to x is sorry implies that x is equal to a inverse b. So we were talking about that, and in which Divyendu said that why we are not looking at direct analytical solution, that is a inverse equal to b, is because it's very expensive. Okay, what do we mean by expensive? That if I'm going to be looking at a matrix that is huge, we are not talking about 5 by 5, 5 cross 5 matrices, or even 100 cross 100 matrices. We are essentially looking at millions of elements in our matrix, right? So such a huge matrix or such a huge system of linear equations cannot be resolved using the inverse, because it is inherently an expensive process, that it takes too much computational power in order to be computed. So we can't use that. All this is a beautiful and elegant solution which we should use when possible. This technique of inversion of matrix becomes impractical. Impractical because we don't have the kind of computational power required to pull it off. We don't. So that becomes impractical after some time. So now we have introduced numerics in two ways. First is that we got these algebraic equations which are forming the matrix by using numerical techniques. Okay, so that's level one of numerical techniques, finding the equations. This numerical techniques. To I used to, what do I want to say? Yeah, I used to come up with the equations. Okay, come up with the equations in our matrix. That is level one of our using numerical techniques in the matrix. And then the second place where we use the support of numerical techniques is now to solve that matrix. Okay, to solve matrix, we use numerical techniques. Okay, so a lot of the numerical techniques that we will be talking about today, we'll be doing some normal solutions. I think we will have time for only for 2 to 3 questions. But the crux of what I want to say is that a lot of the solutions, like the methods that we are seeing today, are used purely computationally. Okay, no one's going to ask you to solve a 400 cross 400 matrix by hand. But why we are going through with the process and how it's solved is that when you're writing a computer program in order to solve your matrix, that time you should know what the algorithm is so that you're able to write the loops effectively. Is that okay? Any doubts? Any comments? So what opinions do you have regarding whatever we have said right now? Okay, so we'll move on. But I would really appreciate it. Yeah, numerical but depend on precision required. Yeah, that's right. Precision required and also the amount of computational power that we have. Okay, so the most precise way to do it would be to actually get the analytical situation, analytical solution. But we've already concluded that that's literally not possible. That's not something that can happen, right? So that's why we were like, let's resort to the numerical techniques to come up with these sorts of these sort of algebraic equations. Then we club together those algebraic equations to come up with a huge matrix. Okay, and in order to solve that matrix, which we could have done by A inverse equal to x equal to A inverse B, we are unable to do so because we don't have the computational power to do it. Okay, so therefore we are using numerics in two ways. Okay, this is the background for what we will be discussing today. Right now, let's see. I'll be properly discussing the entire algorithm for two methods. One is Gauss-Seidel. The second is PSOR, that is point successive over relaxation. Okay, so Gauss-Seidel is something that we've all heard before, and also there is something known as this Jordan technique, Gauss-Jordan. So then that is also something that the other TA must have discussed in some detail, right? So essentially, what are we trying to? We'll start from our matrix equation because our objective for today's discussion is to solve the matrices numerically. So obviously, we need to start with the same equation. We cannot alter that. Let me Right. Okay. So what we do is that we break our matrix A up into two halves. That is L, which is the lower diagonal matrix. So we all know what lower diagonal matrix is. Assuming we're comfortable with that. Okay. And the upper diagonal matrix. Okay. So basically A is equals to L plus U. So I'm going to have this. Then what do I do? Since I'm using an iterative technique. Okay. I'm going to attach my L with xn plus 1. Okay, this is at my future time step. That the time step at which I'm trying to compute this x is equal to b minus uxn. So these are the knowns and this is the unknown. Okay, like we know the matrix L, but we do not know the xn plus 1. Okay, this is what we are trying to find out. That is the solution set, the set of solutions for all of the x at n plus 1. Okay, so now this is a vector. This is not a single variable. This is a vector. Okay, so basically this is a system of equations, right? So this is the this is how we go about with it. Okay, the difference between Gauss-Seidel and Gauss-Jordan is because both of these methods use this form of equation only, is that as and when you have a value for xn plus 1. Okay, when I have xn plus 1 for let's see at I, um, okay, so then I have xn plus 1 at grid point I. Now this is a variable. L as in lower below the principal diagonal. No, that is including the principal diagonal. Thank you. Uh, actually, technically, it's not really a hold up as such, but what we do is that we use it as a lower diagonal thing, like including the diagonal. So basically, we have the lower, sorry, right. So this L is going to be this sort of a thing. So the diagonal is included for L and for U it is not included. Okay. Uh, Sorry. Okay, so we all get the point of what I'm trying to say, right? Okay, so now that I have, when I'm trying to do this sort of a computation, basically I can get, I'll get a system of linear equations as specified, right? So when I have the value for xi equals at n plus 1 at time step, then I'm going to plug it in. Plug it in to my xi plus 1 n plus 1 solution. Okay, fine. So now we'll do a question related to that so that we understand what we mean by all of this. Okay, right. So you're going to have to help me with this, right? Right. One more important point is that you need to know for Gauss-Seidel this matrix A that we have. Okay, A should be, you've taken it in class, right? So tell me the two conditions that Gauss-Seidel, this matrix A should be fulfilling in order to apply Gauss-Seidel. None of them starts with irreducible. Anyway, we'll not bother too much about the nomenclature, but it's called irreducible diagonally dominant. Have you heard of diagonally dominant in class? Right. Okay. So diagonally, okay, great. So what is diagonally dominant? Can you type in the chat box quickly? I'll give you a few options. Is this enough for me? I'm just going to write down something. You tell me if whether that is a sufficient and only condition for this for me to apply Gauss-Seidel. Then the near term one, like, okay, yeah, that's great. Thank you all. Um, Also, one more important thing is that at least one, because of this term irreducible that we have over here when we're talking about irreducible. So there's a mathematical background for all of that, which is not in the scope of this class right now. And also along with this, and one of a any one, this one should have a strict inequality. Yeah, that's great. Devendra, thank you. Okay, so this should have a strict inequality. That's great. I'm happy to know for any I. Any one j, sorry, one I is great, fine. Right, let's look at this question. This is given to me in the form of ax equal to b. Okay, my a is 12 1 2 7 5 7 3 1 minus 11. The question that you asked, Alfarina, that whether we are taking the lower diagonal matrix, including the diagonal or not. The reason for taking the diagonal into the mixes that we are seeing over here when we were looking at the Gauss-Seidel solution, that this L is going to be attached to the unknowns. And whenever we are using this matrix technique, we are always looking at the like we are considering the unknown at this left hand side, that is xn plus 1, and the diagonals are multiplied with the unknowns. Okay, we'll see what I mean in this question, so you will understand why we should do that. B is equals to 2 minus 5 6, and they've given us an initial guess value of this. So that is my x naught, x at So x naught, that is my time step is 0th. Okay, that is my initial condition. That is 1, 3, 5. Okay, so I'm going to break down my A into L and U. 12, 0, 0, 1, 5, 0. Can you invert this matrix for me? Why we'll invert it is because it will make our job easier while we are writing the mathematical equations. We don't actually need to do it in the computational form, but right now since we're doing everything by hand, it's better to invert it. Please give me the value for L inverse. Okay. And once we have the L inverse, we will need L inverse B and L inverse U. Without, no, Dibyendu. Why we are not trying to do that is that would be simply our A inverse B, right? If you want to compute the exact solution, you would do that. But we are trying to iterate. Hmm? I'm not sure. Can you like just unmute yourself and ask the question? We can also iterate. Okay. Anyway, we are looking at this method, which is the Gauss-Seidel method. So that is why we are looking at that. You're saying that we'll be able to iterate. How will we be able to iterate if we do that? Because then our x would be, we simply have A inverse B. Why would you iterate in that case? No, but why would we? We can iterate, of course, but then the thing is that what would our reasoning be? Because if I'm going to invert my A inverse, then I'm just simply going to get this, what I've written right over here, x equals to A inverse B. Do you get it? Like, we'll get the exact solution with that. We are trying to use some starting point after which we will be able to get the further solution. You will be saying that why are we doing this entirely, which is why I told you about all of these things before. Okay, whatever we discussed earlier, okay, that was why we are doing this useless activity with respect to 3 cross 3 matrices, because for 3 cross 3 matrices we can get x equals to A inverse B, and if we iterate in that in this respect, then like what are we using? Because we don't have, everything is unknown on the left hand side and everything is known on the right hand side, and you really don't have any scope for iterating in this thing. If you differ, then you can unmute yourself and tell me how we can iterate with that. L and U decomposition was not taught in the lectures. Okay. How were you taught to do it then? Kushi has an answer for L inverse. Okay. That's not the answer I have over here actually, Kushi. Dibyendu, can you unmute yourself and tell me what was taught in class?
Uh, Am I audible, ma'am?
Yeah, you're audible.
Actually, first equation we can convert x1 in terms of x2 and x3. Similarly,
Okay.
second equation x2 in terms of x1 and x3, and replacing the initial value on the right side of the equation.
Okay, yeah, actually that is right. You are right in that respect, that you are saying that it just instead of using this sort of a, basically we are both trying to say the same thing in like this equation that that I have over here, right? L, this thing, like I have something like this over here, है ना? So essentially,
Yes, sir.
if I have the L over here, then that will give me the coefficient for this lower matrix, right? For this xn plus one. Okay, let's go with that way. Alfrina, you're right. That is the correct method to like that is the correct inverse. So what I was trying to tell you is this might be actually thank you Divyendu for offering a better method. You're saying so basically what Divyendu is saying is that I don't need to go ahead and do all this inverse and everything business. It is costing me too much time, which is true. So what I can do instead is that I can simply look at this equation only, which I had L x n plus 1 is equals to b minus u xn. I know my L, right? L is what? 12. Okay. So for my first one, it would be 12 xn plus 1 is equal to 2 minus u xn. What is u xn? U xn over here is 1. Actually, no. This is not the way to go about with it. Just a second. Oh, thanks, Kushi. Sorry. Yeah. Whole divided by. But then that would change the magnitude. So that's my issue with that. Get it? It will change my magnitude then. Then it won't be the inverse. It would be 12 times my inverse. Like whatever. 12 by 55 times my inverse. Anyway. Okay, just a second. I'll just follow. Devendra, just give me a second. I'll just follow through with what I had already planned up, and then we can have a discussion. Anyway, right. See, we need what Alpharina has because then that will give me the identity matrix. So that's what I need now. L inverse into L equal to identity matrix. That's what I need. Anyway, if you're like, I could be wrong, so just take it with a grain of salt. But then L inverse, what should be the correct answer is over here. So essentially, what you will do is that you will multiply this L inverse with the B matrix to get L inverse B. I'll just write down the final answer. Okay. Hopefully, we agree with that. Right. Then I need my L inverse U. This is this is what I have. You can check the values on your end. Right. Um, Fine. Then what I'm going to do is once I have this sort of all of the requirements from my expression, I will say my xk1 is equal to this thing 1 by 6 minus 31 by 30 minus 129 by 110 into your whatever minus, I'm just going to write down the short thing, into the x naught, right? So from this I'll get three equations because then I will solve it from line by line. Okay, so then I'll say x1. Now I'm doing my first iteration. Equation x1 is equals to k plus 1 by 6 minus 7 by 12 into 3 minus 1 by 4 into 5. This is what I'll get. This is all mathematical things, you can do it. Basically what I'm doing is that I'm decomposing my this expression, which is again a vector and matrix expression, into normal equations. Okay, and then this is what I will get, and then I'll get a first solution. Okay, I'll get a value which I have over here is minus 2.833. Okay, if you want to do it on your own, you can do it right now. I just want to get to the Bendu's question, that is why I'm just rushing a bit. But essentially, what you'll do is that you'll calculate x1 at k plus 1. That is just k plus 1 over here is just simply 1, right? Because it's the first time step. And then you will plug in this value in your equation over here for x1. Essentially, your x1 will evolve into, sorry, this x naught will evolve into x1 1, x naught 1, and x naught, sorry, yeah. No, just a second. Sorry. Basically, what I'll do is that I will keep on replacing the terms in my vector, which is at my right hand side, with my knowns, and the club of my knowns will keep on increasing as and when my xk plus 1 keeps on going. Again, Dibyendu, what were you saying? Sorry.
Ma'am, am I audible?
Yeah, yeah,
Can
you
you
are.
show me the question?
The question is right here.
Yes, ma'am. That from first equation, that is 12x1 plus 7x2 plus 3x3 equal to 2.
Okay.
Then you can write x1 equal to 2 minus 7x2 minus 3x3 divided by 12.
Okay.
Similarly, for second equation, we can determine x2. For third equation, we can determine x3.
Okay. So you are saying that we can just open it up and just say 12x1 plus 7x2 plus 3x3, sorry, 3x3 is equal to 2. And then I can just put these things on the other side, right?
Yes, ma'am. And then
And
determine
work with it.
x1.
Yeah, that's actually right. Thank you. This is a better method. This is how, like, the way that I've shown you is how I have been doing it. But I'll just change up the approach a bit. Okay. So let's go with that. Is that okay? We'll just change our approach a bit and try to solve this question. I'm going to go ahead with that. But essentially, we'll just decompose this multiplication into three equations. So I have x1 is equals to 2 minus 7x2 minus 7x3. Here we are going to substitute the x3 and x2 values from my initial guess. I'll get a revision for x1. Then that I will put for my other two lines. Is that fine? I'll
Yes.
just try to do it. I'm sorry. So this is the method that I have been using, the inversion method. But clearly it's a more expensive method. So for your assignments, you can go with this one. This is a better way to go about with it. So I'll accordingly revise my PSOR method as well. So yeah, this is how you do it. Would you like to solve it right now? We'll just write down the solution. Thank you for the inversions and all, but it seems like it's a bit of it's a bit of a long-winded process. We'll just restart our process. Essentially, we are going to get some equations which are going to look like 12 x1 plus 7 x2 plus 3 x3. So this subscript is the location of the is like it refers to the location, and this thing is the iteration number, the one at top. Okay, so this is going to be 1 is equals to 2. We're going to put 12. Okay, so then you'll get a revised value for x1. Can you tell me the revised value for x1? Okay, minus 2.83. So that's right. Thank you. So then once we get this minus 2.83, we're going to plug it in the second step of our first iteration. So this is the second step of our first iteration where I'm trying to find this. This is my unknown now, right? So what I'll do is that I'm going to plug this value minus 2.83 over here. So what do I have over here? Minus 2.83 plus 5 into x21, I don't know this, plus 1 into 5, which I know from, because that is my, still I'm using the not values for the 3 as well. So here we're going to get another division. What is this division? So this is what we're getting. Hopefully everything is on the same page. And once we have that, then we go with the go for the third one. In this case, for the, when we are looking at x31, we have the values for x21 as well as x11, right? So what I'm going to do is then again write down the equation in terms of that. 2 into 2x1, and this is for what? Minus 0.6 minus 0.634 into 2. Okay. For x2, I'm getting a value of minus 4.434. So if anyone can just confirm. Okay, thank you. Right. So this is like the maths things. Hopefully that will not be too tricky. But our main point over here is that when I'm looking at x21, I already have the value of x11. So I'm going to put it back into my equations. 7x21 plus, okay, so this is my unknown. This I know, this I know, this I know, everything else I know. Okay, so basically this is you're going to be your first, at the end of your first iteration, you're going to get some values which are going to be written by what is over here. Please calculate them for me. This equation, option A. Option A is after your first iteration, Devendra. What are we asked over here? After the third iteration. Sorry, in case because I think I did not read it out. So basically we need to repeat this process 3 times. So you've understood the process. Can we move on to the other method, that is the point successive over relaxation? We don't have much time left. Or should we complete this question? How to start second? Okay. Then once you are done with your first iteration, what is the third thing? Minus 1.997. Okay. So basically now in place of x naught in my equation, my revised, like I have x1. I had x naught equal to 135 to start with earlier. Now I have what is this? Minus 2.83 minus 1.434 minus 1.997 to begin my second iteration. So then when my second iteration comes, same equation will come. The equation will not change, right? Let's just copy this over here. For my second iteration, I have this over here. And now, instead of these ones that I have over here, I'm going to have like the 0 is going to be replaced by the 1, because now that is my known. This is my second time step. And this unknown is going to be 2. Please recap the process. Okay, then I will go with the second iteration. We'll extend the class a little bit. Fine. So basically, what happened is that we tried to write like whatever matrices that we have over here, which is a 3 cross 3 matrix. We tried to like matrix equation. We wrote them down in terms of the linear equations that are the constituent linear equations, and then we said that we have the x1, x2, and x3 values at time step 0. How do we have that? It's because it's given in the question. Assume the initial guess values as x1, x2, x3 equals to 135. This is my x naught. So this is my x naught. Okay. When I'm writing not above, that means the time step is 0. Okay. This refers to x naught is time step location. Okay. Right. So essentially, I have my x naught available with me. So what I did is that for finding out my x1, that is my unknown, I wrote down my equation as it's supposed to be, and then I said, okay, for the x2 and x3, I'm going to use the naught values instead of the 1 values, because I don't have the 1 values, I have the naught values. That is a time step 0. Then I computed my x1 accordingly. Okay. Then once I have my x1 at the first time step, I can use that. I can plug it into my equation for finding the x2 at the first time step. So what I did is that I again once again I went with the normal equation, that 1 into x1 plus 5 into x2 and everything. I found out my linear equation which corresponds to x2, but to the second row, and then what are my knowns over here? My knowns, I'm going to be, I'll just outline that in pink, the knowns. So x1 I know from my last iteration, x naught I know because that is I'm already given by the question. Okay, and then I computed the x2. So basically, you see what I did, that instead of using this naught value over here, which I also could have done, I have used x1 1. Why have I done this? Because this is the method for Gauss-Seidel. In case you had written x1 naught, if you had gone with this instead of using the already computed value, that is x1 1, then that would be the Gauss-Jordan method. Okay, which we've done earlier, like in the last TA session, the Jordan method must have been discussed, right? So the advantage of this Gauss-Seidel is that it converges faster. Okay, why does it converge faster? Because whatever corrections I'm making by computing the iterative values of x1 at a certain time step, I'm putting them back into my computation for the next time step. Is that okay, Akshat? I will just go through the second iteration properly so that we have a clarity regarding that. So now in the second iteration, this is my unknown, because we have the, okay, great. We have the values from x1 and from x1, since that has been computed by our last time step. Then you will repeat the process. Then once you get your x2 1, okay, then you will plug it back into your second, that is x2 2 values, the x2 2 equation. So in this case, again, the ones that are marked in pink are the knowns. Okay. And then so on and so forth, you will compute everything. Okay. If you want to quickly go through the process, you can go through it right now. Otherwise, we can move on if you understood what to do. If you use 0 in all three equations and modify in second iteration, it will converge slowly. Method is called Jacobi. 0 in all three equations? Yeah, you're right. Huh, you're right. Basically what he's saying is that if you use the values of, if you do not update the values of your x1, x2 and x3 as you keep on computing them, then you call that method Jacobi. Okay, that will converge slowly, right? Why it will converge slowly? Because you're not using your corrections again and again. Okay, so this is the method for Gauss-Seidel. Okay, next we will go on with the PSOR method. I'll just mention it briefly, like I did with the Gauss-Seidel, but we'll just do it quickly. PSOR. Are we all on the same page? We are okay. We can move on with the PSOR. Okay, I'm going to assume yes. Fortran code of exam. Yes, I do. Alfarina, please write me a mail. This is my email ID, ae19d752@gmail.com. Sorry. Just and I would suggest instead of just like trying to get a code from me, you can develop one on your own. I don't have a Fortran code for like simplified Fortran code for Gauss-Seidel, but I have a simplified Fortran code for I have a simplified MATLAB code for Gauss-Seidel. Okay. So if you're comfortable with MATLAB, you can do that. Otherwise, we can discuss it. You can just write me a mail. We can develop a code. It's going to be fairly simple, right? PSOR. So then PSOR is similar to the Gauss-Seidel method, but it's like a sort of a modified version of it. This PSOR means point successive over relaxation. Okay, why do we over relax? And what is over relaxation? Over relaxation. First of all, we over relax in order to get quicker convergence. Those of you who would have worked with ANSYS Fluent would have heard of something known as under relaxation factor, right? So we put an under relaxation factor in order to slow down the solution so that it becomes more stable. Okay, so under relaxation is done to make the solution more stable, and over relaxation is done to make the solution more quick. Okay, so it converges quicker. So essentially, once again, we'll begin with our equation that we were talking about earlier. So instead of decomposing it into L and U, see why we were talking about that L and U decomposition is essentially that L that we were talking about over here is the coefficient for the unknowns, and the U is the coefficient for the knowns. So that is exactly what we did by modifying our method from this long driven method into the simpler way to do it. Okay, but the crux of the matter in this case as well is that basically you are deciding what your coefficients are going to be, right? So coefficients for the knowns were the lower diagonal thing, but here we're going to just decompose our A into a diagonal, into a lower diagonal matrix, lower triangular matrix plus a diagonal matrix plus ux. Okay, then what you do is that you just that again you decide where you want to put what. So then this D has to be partnered with both the upper and the lower diagonal matrix when we are going to put it equals to n plus 1 as I need. Okay, let's just not talk about that. I'm going to multiply it with a factor that is omega, that is my over relaxation factor. This is the derivation part. So essentially, when we simplify all of this and we decide which are going to be the coefficients for the xk plus 1, sorry, the current time step versus the past time step, then we choose that the diagonals only, okay, diagonals only, this is going to be my k plus 1, this is going to be my k, this is going to be my k, this is going to be my, so this is going to be my k plus 1. Why this is k plus 1? Because again, these are the coefficients of the unknowns, the ones that we don't know, since we have not completed the computation for those ones. So once again, I'm just modifying the method a bit to make it more simpler to compute. Then diagonal terms will come over here. Let's write that as ai into pi minus summation of aij. In this case, j is less than 1 is because again, this is the lower diagonal part of the matrix. The lower diagonal part of the matrix are the coefficients for the terms that we do not know. Okay, because we've not completed the computation for them yet. Are we okay? Are we on the same page or did I say something wrong? Okay, essentially this is your equation that you will be using for solving PSOR. Okay, so we'll pick it up and we'll go back and use it for our equation, for our questions. Okay. So here let's read the question first. Determine the value of x1, x2, x3 using point successive over relaxation method for question 12, that is the same matrix that we have over here, up to 3 decimal places for the 4th iteration. We'll not go that far, but we'll just do the equation. Omega is 1.25. So then what do I know? I know that my omega is 1.25. I have all of my xiks, that is xi naughts in this case for the first iteration. Once again, for the first iteration, so then we'll just begin the first iteration by using this formula that I've written over here. Okay, so let's see, x, I'm looking at the first step, is equals to 1 minus xik. What is xik? Xik is once again the x naught, okay, xi naught plus omega by aii, that is the diagonal term for that, for my diagonal. So in the previous case, what was the diagonal term for the 1 1 diagonal? The 1 1 diagonal was 12, right? Yeah. 2 minus summation of, now j is less than 1. So j is not less than 1 for less than, I've written 1 over here, sorry. I am. Huh. J is not less than 1 at all because we don't have a location for x0. So then this term, we don't have our second term at all. Okay, we don't have that second term. Then we say Aij. So Aij is for j is more than 1. Should copy just this. Aij, j is greater than 1. So j is greater than 1, j is 2. 7 into, now I have xk, that is x naught. We will be using the x naught. X naught is 3. Okay, x naught 2, that is. See, why am I doing this 7 and 3 thing? Is that 7, this corresponds to the x naught 2, sorry, x 2 naught into a I2. Okay, this is what I have. This is what I needed. Plus A13 into x3 naught. This is what I needed. So then I'm just doing that by using my formula. Into 3 into 5. Right. And omega is 1.25. Xi naught is 1. Okay. So you will get your x11 from here. Okay. Once you have your x11, you're going to use the same formula for x12. How are you going to do that? Is that you'll just simply look at the formula. You'll say my time step is 1, equals to 1 minus 1.25, that is 1 minus omega xik is xi naught, the x2 naught is 3 for me, plus 1.25 by, what is the diagonal term for the second one, 5 into 2 minus 2, not 2, bi minus 5 minus, now for this the second term is j is less than I. Okay, so j is less than I. What does the j is less than I mean? That j is 1, because my I over here is 2. So then I'm basically looking for the term I21. Okay, where is I21? I21 is 1. I'll say 1 into 1 into what was this value that I've already computed, xi1 minus of 1 into xi x3. Okay, so we understood this was for the, we need the summation for this summation, right? So then we got a12 into x 1 at 1. Okay, and then we have over here x23 x3 naught. Okay, this is what we are having, and then we'll continue to keep these iterations in a similar fashion in order to get our results. Once again, we'll keep on substituting the already computed values into the same time step. This is for PSOR. This is the method for that. We are out of time, but hopefully the method is clear. This is the method for, like, straight away a line method. Okay, so we don't have to like worry too much about what to do with respect to the decomposition of the matrix into diagonals and L and U. But why my motivation behind telling you all of this thing, which we have over here, is so that we understand where all of these equations and all of these methods are stemming from. Is that okay? One more thing, for stability in this PSOR method, for stability, that is, the solution should not diverge. Okay, omega should be from PSOR. Okay, so in case you are asked to select a over relaxation factor which is like 2.5, then don't do it because it's not going to be stable. Of course, you can do it if the question demands it, but then the thing is that that would be to demonstrate the point that this is not stable. Right. Since we are out of time, I'm going to be ending the class soon. Hopefully, the method is clear. If you want to resolve them right now, we can continue with the solution for another 10 minutes or something. Otherwise, we can move on with any questions or any comments that you might have. So today we basically implicitly looked at three methods: Gauss-Seidel, Gauss-Seidel, Jacobi, and as well as the PSOR. Okay, Jacobi is when you do not update your solutions with the when you are computing for the same time step. Gauss-Seidel is when you keep on updating your solution when you're computing for one time step, and for PSOR you essentially have an extra factor of omega. Okay, what is TDMA? Okay. TDMA is Thomas algorithm, as Dibyendu has said, that is applicable only for tri-diagonal systems. Okay, see that is not something I can do with pen and paper. That you need a code for. Okay, at least I can't do it. Let's have a look if we will be able to. I'll just talk about it briefly. TDMA, ADI is also there. I forgot to mention that. TDMA is what we have a problem with, right? TDMA. So TDMA is applicable. Pentadiagonal system. Hmm. No, TDMA is applicable only for tri-diagonal systems is what is to my knowledge. But then Akshat, I'll just come back with that. But in my opinion, it's applicable only on tri-diagonal systems. TDMA. Right. So this Thomas algorithm and TDMA are the same thing. Yeah. It should be only for tri-diagonal systems. Right. Okay. So this will be applicable when you have a tri-diagonal system. For tri-diagonal system looks something like this. You to have A11, A, and then this is going to be populated, this is going to be populated, this is not. Okay. So even if it's a bigger matrix, then also it should remain. Pentadiagonal system is converted into two diagonal systems using ADI. Okay, so the baby has an idea about that. Okay. Thank you for that. Into two tri-diagonal systems using ADI. So ADI is sort of like another iterative scheme in which we sort of sweep through the matrix. So we can take up ADI in the next class if that is required. I don't have enough time, and I don't know, and I need to really revise this in order to do it justice. But my elaborate in the class the diagonals are pentadiagonal systems. Akshat, we'll have to take it the next time. If that is what you need, then I'll just write it down and then I'll take it up in the next class. Is that okay? Thank you. Thanks a lot. So let's write it down. When is the submission date for your week 4 assignment? 24th. Okay. Oh, okay. So what I'll do is that I'll make a PDF for the explanation of the pentadiagonal system and I'll upload it onto the Google Drive. Okay, you all have the link for the Google Drive. I'll just put the link